All right, so what I want to do here for 242, it's week 8, and unfortunately I'm going to have to leave a little early. Tim's going to be here for a couple hours next week and go over some of the quiz. A few people said they had real struggle with this last quiz, so let's just dive into it right now. And it was long, it was challenging. Looks like 2 people have attempted it out of the 12 in the course.
I don't think I have attempted it.
Yeah, well, let's just take a quick look. I'm going to take a pause. It's just an overview of everything in the first couple of chapters. Let me pause. Oh, I think I forgot to record there. Okay, let's just review what we just went over. So, absorber, the gross area and the aperture area. Again, one's the biggest, one's the smallest, and one is in between. That's in the book. It's fairly self-evident, but check that out. Unglazed means there's no glass on the solar thermal. That's also fairly straightforward. What I just explained here is when a photon, here's your photon coming in to your chunk of solid matter, which is right here. It's either going to be reflected, so it's going to come in and bounce off. That's rho. In general, that's a bad thing. It's going to go straight through. That's alpha, also not good. Tau is, shoot, sorry, back up. Got ahead of myself. New page. It's all Greek to me. No, here, let me just redo that. So here comes the photon. I'm going to call that phi. If it bounces off, that's rho for reflection. If it goes through, I just reversed those two. If it goes through, that's T for transmitted, which you also don't want. If it comes in and stays there, it's alpha for absorbed. And only one of those 3 things can happen. It's absorbed, it's reflected, or it's transmitted. So first law says they have to add up to 1. They have to become unity. So that's where that is coming from. Now, in the solar thermal book, there are these G's and G naughts. Let's just take a quick peek at that. Yeah. So we actually have done this in class, and it's in the previous lectures. But here's the figure you're looking at to answer that one in the book. It's figure 210 on page 25, and so. G naught is the total radiation coming in. G1 is what's reflected from the glazing. G2 is reflected from the absorber. Q2 and Q1 are the heat that are flowing out of the system. So the G's stand for the radiation that's bouncing off, and the Q's are heat flow. Some of which is lost, and what we're looking to maximize is Q sub A, which is the absorbed energy. All right. Then just below that, figure 211, that's also on page 25. Show it right there. There's a little chart. And really all you're doing there is extrapolating. So you've got the efficiency maxes out at about 80%, and it's showing that for a greater temperature difference, you just have more sunlight. It's just so as more sunlight comes in, you get greater power. Nothing all that earth-shattering about that. This is just looking at the figure and determining for the 600 watts per square meter and a temperature difference, just dive over and find the efficiency from the graph. Oh, So this is another good one. What you're looking for here. Yeah. So what you're looking for here, you've got Q dot, so this is the heat flow, equals K.
First derivative?
This is just heat flow. I
Okay.
mean, it's the time derivative of heat, so it's thermal power. Thermal power equals K times the area times the change in the temperature difference. So in this question, we know Q dot equals 50 watts. We're given the area and we're given the delta T. So we know that, and you can just, it's one equation, one unknown at this point. You get K on the left-hand side of the equation, and you've got it. Well, I guess it's time to do something. Okay. EBAD, I'll let you look that up. I'm not going to tell you the answer on that one. Which of the following turbines is most likely to produce the greatest amount of torque in a modest wind? So whenever I'm faced with a situation like this, you might just say, well, here's sort of the simplest turbine you could have, just a one-bladed turbine. Here's another one, and then just kind of keep moving up, and then then get to a pinwheel. You've probably seen a pinwheel before, child's toy. Think about what that thing looks like. So that's how to solve that problem. Yeah, this one, two-bladed turbine that is yawing in the wind. Why would it be jerky? So here's the deal.
Those are from the jaw text.
Yeah, it is. Yeah, this is chapters 2 and 3 of both books.
Oh.
Yeah, and it is in the jaw text. And so as this thing is spinning, let's say the wind is coming here, but now the entire turbine is going to rotate. So I've got this, here's my hand, the turbine is just spinning this way, but instead of, the wind blowing from right to left, now it's going to blow from front to back. So the question asks you to determine what would make that thing wobble as the blades spin around. Yeah, so Gary's like, I know I read
That's
it.
in the,
That's right, it's just right there.
that's
In
in the
the,
Peugeot text,
I think it is in the Peugeot text also.
because I blasted through it again the other day.
Yeah. Well, that should
Very interesting.
strike your memory. No, I love that book. I love that book. Okay, select the statement that most accurately represents reality. Yeah. Okay, let's do that really quick. That's a good one too. So if I'm let's see, what's the best way to this is really a three-dimensional problem, which should give you a reasonable estimate of the answer. So I'm going to try to draw this three-dimensionally. So this is the velocity of the wind, and let's just say the velocity of the wind in the z direction equals 0. The wind is not blowing up. Let's let this be the x direction. The velocity of the wind in the y direction also equals 0. It is not blowing into or out of the page. Right? So the velocity of the wind in the y direction is greater than 0. It's blowing at the wind turbine. So here's the nacelle. Here's the blade. Here's the other blade. Now, as this thing spins, well, it's spinning like this. So the velocity of this top blade, let's say it's coming towards us, the velocity of the blade on the top in the, let's see, X, Y, and let's have Y going into the page. So I'm going to draw that as an X. If it were coming out of the page, I'd draw it as a 0. So the Y direction is pointing into the page. The negative Y is pointing out of the page. So the velocity of the blade of the turbine in the Y direction is less than 0 because it's going into the page. Here, since it's so the bottom, since the top is coming out, the bottom is going in. The velocity of the blade at the bottom in the Y direction is greater than 0 because it's going into the page. So the wind is coming over here in this direction. The blade is coming at you. So from there, you should be able to determine how fast this tip is going relative to the wind. And let me just give you one vector example. So if I had two cars, this is V1, and I have another car coming here, V2. V1 plus V2 looks like this. Looks like the V1. You add the V to it, to it, and this is the relative velocity. So there's V1, there's V2, and this is V1 plus V2. So it's a Pythagorean problem. Yeah, exactly. So if you had another car that was going exactly the same velocity in the same direction, their relative velocities are 0 because they're going side by side. Okay, what's next? Let's just dive into the problem. Yeah, so these are all aspects of a wind turbine. So you can look at that guy V and say, okay, that's going to be some velocity. You can see that P down here is going to be pressure. This is more or less process of elimination. So if I were taking this, I would just kind of look at them, grab the easiest ones first. A lot of times U is used instead of V. Sometimes when you're looking at velocities, so that was all that was on that problem. Sometimes when you're looking at velocities, let's just say I had a velocity in 3 directions. I might have U, V, and then W. So if I had some other velocity up in here, the velocity total would equal U plus V plus W. So that's something you'll see in the textbook too. Instead of using a V for velocity, use a U. All right, that's all I got for today. I will upload this, and Tim's going to teach Tuesday, Thursday next week, and I'll be back from DC. Thanks.